We're now going to go back to the computer where we're going to process our field data, and we're going to finish the processing with a sequence which was acquired using the data set acquired as 3 separate lines of data, which we will merge into one continuous data set, which will be approximately 72 meters in length. This slide is a typical seismic refraction record, which will now explain what we're seeing on the screen. Across the top we get our geophone numbers from 1 across here to number 24. The second row, which we'll see later as we make some adjustments, is our trace scaling factor, which is applied to each of the geophone channels. You'll note initially that the numbers here on the left hand side of the screen, which are in the 70s and the 60s, etc., and as we come across here to the right hand side of the screen, get gradually smaller. So the number here on channel number 24 is 46, and this designates that we're showing a smaller amount of amplification on these channels. The blue horizontal lines are travel time lines, and along the x-axis on the left hand side of the screen we have the travel time in seconds, from 0 down to 1/2 of a second at the bottom of the screen. What are we seeing on the screen in terms of our wavelets? If we pick channel number 13 as a typical channel, first of all, in this portion of the record we have some high frequency wavelets, and these are P waves. As we come down we get to some larger amplitude wavelets, and these are also lower frequency. We can tell they're lower frequency than the P waves because the distance from the peaks here to this next peak is greater than the typical distance from a peak to a peak here. So these are lower frequency waves, and these are what we call surface waves, which are a form of shear wave. In a seismic refraction record we're not interested in these surface waves at all. These are important in a different type of seismic surveying which is beyond the scope of this tutorial. In refraction we're purely interested in the travel time, which is the time taken for the P wave to travel from our shot point, our hammer point, which is designated by our T0 point here, which is our first horizontal blue line, and the travel time to go from here down to this point where the line deviates from being a straight line. And this point here, which I'm showing with the cursor, is called our first break point, otherwise known as our first arrival point. In a seismic refraction data acquisition sequence, it is important that we can very accurately locate this time for our first breaks as accurately as possible, because it's only by achieving high accuracy in this travel time that we get the best fidelity in our data analysis. So, as we're displaying a very long record length at the moment, 1/2 a second, and our travel times are only of the order of 0.05 of a second, probably what we need to do is expand our record. So if I come to display shot parameters and display boundary, I'm now going to reduce the amount of time that we're showing on the screen to about 0.2 of a second. We've now expanded the data, so we're only looking at the top portion of the record, and we can now determine our travel time to this first break with a greater degree of accuracy. You can also see here that this line here is much flatter than it is if we come over here to, for example, channel 6, where we're getting some very low frequency noise on the data. This is because as we move further away from our shot point, which in this case is nearest to channel number 24, the waves spread out in many different directions. So the amount of energy arriving at any one particular geophone gets lower and lower as we move away from our shot point. Technically this is called spherical divergence. And what it means is, as we get further away from our shot point, we need more and more energy to build up in the geophone data channel in order to achieve a good a signal to noise ratio as we possibly can. With a modern seismograph such as a geode, all we simply do is stack more times with the hammer, which allows us to build up a good signal to noise ratio so we can see these first arrivals with a greater clarity. Once we've got the data in the memory, and if we've stacked a sufficient number of times, we can possibly clean up our data a little bit by coming to display, shot parameters, and maybe applying a display filter. If we think that we got low frequency noise on the data, we can apply a low cut filter. In this case, I'm going to apply something like a 25 Hz low cut filter, and we'll see what the effect is. Here we can see that the amount of low frequency noise which is coming into the data before our first arrivals is less, and we can now pick our first arrival points with a greater accuracy.